Okay, thank you for the introduction. So today I will talk about the work with Mohammad, Adam O'Neill, and Mingyuan Wang about the black box complexity of private key IPFE. So IPFE stands for Inner Product Functional Encryption. But before we start with that, I want to introduce some very basic cryptography. And probably the most simplest thing you can think of is secret key encryption. So in secret key encryption, we have a sender, Alice, and a receiver, Bob. And both of them have a common shared key called K. Think of this as some uniformly random bit string. And Alice has a message M that she wants to send to Bob over a channel, but she does not trust this channel. So she's worried that someone else might listen into this channel and record what she sends there. So what she can do is she can encrypt that message with her key K to get a ciphertext, and I denote the ciphertext C and then in brackets M. But importantly, when you see the ciphertext, you don't see M. And Alice can send the ciphertext to Bob, and Bob, using the same key, can decrypt that ciphertext to recover M. And yeah, the important property is if you don't know this key K, then the ciphertext should not tell you anything about the message. And of course, if you know that key K, then you should be able to recover the message completely. And so what this gives us is kind of an all or nothing encryption scheme, meaning that if you know the key, you learn the entire message. If you don't know the key, you don't learn anything. And for the traditional application of cryptography, where you want to communicate via an insecure channel, that's completely sufficient. But we will see soon a more modern application of cryptography where this might not be enough. The main focus of this talk is secret key encryption, but since I mentioned a few times public key encryption, I also briefly want to introduce it here. So public key encryption is almost the same thing, except that we use a different key for encryption than for decryption. So the decryption key is now usually called SK for secret key, and Alice's key is called PK for public key, and it's called public key because that key can be public, so everybody is allowed to know it. Okay, so what's the problem with secret key encryption or public key encryption? Well, consider this scenario. Alice wants to store some data in a cloud server. But she does not trust this cloud. So what can she do? Well, she can encrypt her data before sending it to the cloud. So Alice could locally sample her secret key and then encrypt her message M with that secret key and send just the ciphertext to the cloud. The problem when you do this is when Bob arrives and says, I need to know some information about that message M that you encrypted in the cloud. So think maybe of M being some big database of sensitive user data, and Bob here wants to know some function of that database that's actually fine to reveal to Bob. So maybe Bob just wants to know something like, what did the maybe M is a huge customer database, and Bob just wants to know how much did the average customer spend in the last month or something like that. So Bob could, of course, obtain the ciphertext or the encrypted database from the cloud because the cloud has a lot of bandwidth, but that doesn't help him because, it's encrypted. So how can we help Bob to compute f of m? Well, one easy way to do it is Alice could send the key she used for encryption to Bob. But that would be a huge privacy violation because Bob now learns the entire message M and not just f of m. So in the example where this is a customer database, this would not be a good idea because Bob learns now way too much. Another approach would be that Alice downloads the ciphertext again from the cloud, decrypts it, computes this function f of m herself, and sends the result f of m to Bob. However, that would mean a lot of work for Alice, and it kind of defeats the purpose of having a cloud in the first place because now, for example, also when this database is updated, every time Bob wants to know f of m, basically Alice has to do all the work. So ideally, we would want something to give Bob here some partial access so that he can compute f of m on his own, but doesn't learn anything else about the message. And that's where functional encryption comes into the play. So functional encryption is a fancy encryption primitive that allows you to solve this problem. And so in functional encryption, we have one key generator. That key generator initially generates a master secret key, and in the public key setting also a master public key. And then the master public key or the master secret key, depending when you're in the public or secret key setting, can be used to encrypt a message M, very similar to how we've seen this for public key and secret key encryption. And then again, you get a ciphertext for M. So far it looks almost the same. But decryption now works a bit differently. So for decryption, our user Bob can ask this key generator, or whoever has the master secret key, to generate him a secret key for a function f. Then this party can check if Bob should have access to the, should have such a secret key. And if he decides yes, he can use his master secret key and this function f to derive a so-called functional secret key. And this functional secret key he can send to Bob. And when Bob tries to decrypt with this functional key the ciphertext, he doesn't learn the entire message M, he just learns f of m. So that's what we would have needed in the previous scenario. And a security guarantee, I will talk into this later in a bit more detail, but as general, we want security against an adversary who is able to obtain several of these functional secret keys. And then if we give this adversary also a ciphertext of some challenge message M, this adversary should only be able to learn about this message M what he's supposed to learn from the functional secret keys he got, but he shouldn't learn anything else about the message M star. Okay? So now we can solve the scenario I presented above. So when Bob comes here into the play and says, I need to know f of m, then we have a very simple solution. Alice just generates a functional secret key for this function f and sends it to Bob. And Bob can then download the encrypted database from the cloud and compute f of m on its own. And when the database is updated and Bob wants to know the updated f of m, he can just do the same procedure again. And Alice is not really involved anymore. She just has to, at one time, generate this functional secret key. Yeah?
And does this all happen in over secure channels? So the adversary cannot be in between?
Yes, so we are assuming always that channels are authenticated so that no one can interfere somehow with what message is sent. And of course, also at least here, this functional secret key, that should also be confidential because, well, if you learn it, it allows you to partially decrypt the message M. For these channels, we don't care if they are confidential because it's just a ciphertext that you sent there. Okay, now, since I've just defined this, I think a very natural question is how can we get such secret key functional encryption schemes? And in particular, are they maybe easier, are they harder to build than just secret key encryption, or are they just as easy? And since I also briefly touched at the public key variant, another natural question is, or what we know is that secret key encryption is a lot easier to build than public key encryption. So you could also ask if that carries over to the functional setting and if secret key functional encryption is easier to build than public key functional encryption or not. And more general, you might ask, what are the minimal assumptions for secret key functional encryption? So I'm saying here assumptions because in cryptography, we always need assumptions to build things. And kind of one of the most basic assumptions, without that assumption we can't do almost anything, is that one-way function exists, or equivalent that secret key encryption exists. Then I've already mentioned public key encryption, which is a bit stronger than secret key encryption. And even stronger than that are maybe some algebraic problems in cryptography, like hard lattice problems or problems in cryptographic groups that you might have seen. And so we want to understand where does a secret key IPFE sit here, what kind of assumptions do we need? And to motivate that a bit more, I want to briefly talk about the bounded collusion security model. So in the bounded collusion security model, we assume that there's a bound on the number of functional secret keys that an adversary gets. So this bound is fixed in the beginning, and then you set up the scheme according to this bound. So think of it like the adversary can get 100 functional secret keys, but we don't want any security guarantees against an adversary that gets 101 functional secret keys. If that is fine for you, then this question has been answered before. Yeah?
How do you define one function? Because I can define one function as something that outputs 100 things.
Yeah, good point. So for most schemes, we have restriction on what kind of functions are allowed. So you basically cannot define a function that outputs all the things you want, maybe. Another variant is that depending on how you define security, you can do it in selective or adaptive way, and at least in the adaptive setting. You can decide which function you want to see depending on your previous secret keys you obtained. So again, this doesn't work.
Is there a class of functions that you're working over, like linear functions?
Yes, that will come in a few slides, but yeah, essentially linear functions. Or the main part of the work is about linear functions. Yes. Okay, so back to this bounded collusion setting. So in the bounded collusion, the setting has been answered, and it has been shown that bounded collusion public key function encryption is just as hard as normal public key encryption, and bounded collusion secret key function encryption is just as hard as secret key encryption. So there's a very nice and simple answer to this question. So for the rest of the talk, I want to talk about the unbounded collusion setting, where this becomes a bit more difficult to answer. And in particular, now I want to look at functional encryption schemes for specific functionalities, what I briefly hinted on. And one very simple function class that you could allow are point functions. So in point functions, or a point function is just a function that has some default values on all possible inputs except for one. This first part of the input that's typically called in this context identity. And if that identity matches some specific value that's hard-coded in the function, then you get some kind of the second input here that's typically called the message then. And this functional encryption for point functions is usually studied under the name identity-based encryption. And for identity-based encryption, we know in the public key setting, it's actually a bit harder than just public key encryption because we don't know how to build it, for example, from generic groups or from trapdoor permutations, but we can get public key encryption from these assumptions. But there are also good constructions, so for example, from pairing groups or from lattices. But when we look at identity-based encryption in the secret key setting, it actually becomes trivial, and you can get it from just secret key encryption. So here we see when we go from the public key setting to the secret key setting, it becomes a lot easier. And what the main part of this work is inner product function encryption. And inner product function encryption is essentially linear functions. So we now want to allow functions where your message is a vector, your function is also described by a vector, and the function value is just the inner product of these two vectors, mod q, where q is some prime. So we are working over a prime order field. And there are many constructions in the public key setting for this, for example, based on groups or on lattices. So it seems that, at least in the public key setting, it's actually a bit easier to construct than identity-based encryption. So you can get it from weaker assumptions. But in the secret key setting, there are no constructions of IPFE that use anything weaker than what we need anyway for the public key setting. So this is what we try to study in our work, and our main result is an impossibility result. that shows that secret key encryption is not enough to build inner product functional encryption. At least if you are allowed to use the secret key encryption only in a black box way. And this kind of restriction is very natural and almost always happens in impossibility results in cryptography because we cannot really hope to show that secret key encryption does not imply secret key IPFE in the sense of logic, because secret key IPFE probably exists unconditionally. I mean, we have very plausible assumptions from which we can build secret key IPFE. So when these assumptions are actually true, then secret key IPFE just exists. So how can we show a meaningful variant of this problem that secret key encryption is not enough? We can do this by restricting the construction to a so-called black box construction. And what that intuitively means is, well, we are considering only constructions of secret key IPFE that use the secret key encryption as a black box. So they just can use the functionality provided by secret key encryption, but the construction is not aware of how the secret key encryption internally works. So how exactly which circuit is used for encryption and for decryption and things like that. And the vast majority of constructions in cryptography are black box constructions, so such an impossibility result is still meaningful. Okay, then next, our main result is that there exists no unbounded collusion secret key IPFE in the so-called random oracle model. So random oracle model means we want security against adversaries that have as many time as they want, so we have unbounded adversaries. But both the scheme and the adversary get access to a random oracle. So the random oracle is basically something they can call. They can provide any input to this oracle, and as response, they get a random string. And the important thing that makes this useful is that when two algorithms call the random oracle twice with the same input, they will get the same answer. Yes?
Can you go back one? Sorry,
yeah.
Trying to internalize this. So what you're saying is you want to show that there's no construction of SK IPFE that uses SKE as a black box?
Yes.
And has no other assumption?
Yeah, exactly. It has no other assumption, so it can only rely on the security of the SKE.
So the fact that SK IPFE exists, it uses some other assumption.
Yes.
Okay. So you want
Yeah. And yeah, so now this might seem very abstract. Why do we study this in this rather strange model? Well, that's because in 1989, these two people, Impagliazzo and Rudig, they showed in a seminal work that actually showed what I mentioned before, that public key encryption cannot be built from secret key encryption. They showed this in this model and basically showed that if you show such a result, that means there exists no unbounded collusion black box construction of secret key IPFE from secret key encryption. So basically this random oracle model is our model of using a secret key encryption in a black box way.
So
yes?
I'm familiar with this, but I think the way that you wrote it could be confusing because Impagliazzo and Rudig didn't prove that.
Yeah, I mean, they showed it more, yeah, they showed more general that if you have security in this model, that means you, or if you have an impossibility result in this model, that means you cannot get a black box construction for secret key encryption. Okay, so that's basically what we have to do now. And I briefly mentioned very informally before the security that we want for functional encryption, so an adversary that can get as many secret keys as he wants. And here's a more formal game, and that's also the game that we use in the impossibility result. So these security notions in cryptography are usually defined via games between an adversary that's here on the right and a challenger that's here on the left. And for secret key IPFE, that game can, for example, proceed as follows. So the adversary selects in the beginning a bunch of vectors. One special vector v star and several vectors v1 to vt. And he has to take care that this vector v star is not in the span of v1 to vt. And then he gets a functional secret keys for all of these vectors v1 to vt that he picked, but he does not get a functional secret key for this vector v star. And then in the second phase of the game, the adversary can make a bunch of queries. These queries have no inputs, but as response, he gets a ciphertext for a random vector wi, and also some kind of test value, mi star. And this mi star is either the inner product between this wi and this vector v star that the adversary picked in the beginning, or they are just random values that have nothing to do with wi or v star. And the goal of the adversary is to distinguish these two cases. So we will, in 50% of the case, we will use this variant, and in 50% of the cases, we will use this variant. And if the adversary can guess correctly which variant of this game he's playing, he wins the security game. So let me briefly mention here. So the security game makes sense because the secret keys that the adversary gets here, they actually should not help in solving this problem when v star is not in the span of v1 to vt. Because then this inner product depends on basically some component of wi that's not revealed when the adversary decrypts with these secret keys.
So in like the CCA2 setting, there's a phase before this where the adversary can do some of these queries before they commit to their V's, except the V star is partly.
Yes.
Is there not
This is a CPA variant, so the adversary has no decryption oracle or anything. And in general, like for the impossibility result, we try to use a security notion that's as weak as possible, because that makes the impossibility result stronger. So also this is maybe not the most natural version to define security, but it's tailor-made for the impossibility result and basically the weakest we can get. So in reality, you would probably want maybe here not only the adversary gets encryption of random vectors, but more meaningful would be when the adversary can actually choose this vector, has some means at least of getting a ciphertext for a chosen plaintext vector. So we don't allow that here because we don't need it for the impossibility result. Okay, so what we now need to show, or what we want to show, is that a secret key IPFE in this random oracle model cannot satisfy the security notion. So we want to give an attack in this random oracle model that breaks any secret key IPFE with respect to this security notion. And I want to give you a high-level overview how this works. So the idea is that we consider an adversary that makes a brute force search for the secret key for V star. And that might look strange, but remember we are working in a model where we have unbounded runtime. So making a brute force search per se is not a problem. Now with each of these candidate secret keys, the adversary will try to decrypt all of the ciphertext he got in the second phase of the game and compare the solution he gets when decrypting with this candidate value that he got from the game. And if he finds such a secret key where this check passes for all ciphertexts, then the adversary guesses that he's in the game where he got the correct test values. And otherwise he guesses that he's in the variant where these test values were just random. So that this works so far. Let me explain why this works so far. So imagine we're in the variant of the game where we get the correct test values. Then at some point during this brute force search, the adversary will hit by chance the correct secret key for V star. And with this secret key, all of these checks will pass, so the adversary guesses correctly. On the other hand, when all of these test values are just random strings, and the adversary makes enough of these queries, like much more than the size of the secret key for V star, then it's very unlikely that the adversary will find any possible value for secret key V star that matches this test. So this adversary is actually very successful. The only problem is, he runs now for lots of these secret keys this decryption algorithm, and this decryption algorithm might make these random oracle queries. So this adversary is actually making too many random oracle queries. So we have to come up with a solution to that. And the main idea is that we want to run this decryption algorithm and simulate these random oracle queries. I mean, a random oracle is not hard to simulate. Whenever you get a query, you just give a random response. The difficulty is that this has to be consistent with the queries that were already made during the generation of this ciphertext or this functional secret key. For the purpose of the talk, I will ignore the queries that were made during the keygen algorithm, so during generation of the secret key V star, because they're actually relatively simple to handle. The interesting part is how we handle these queries that were made during the encryption of each of these ciphertexts. So we have to make sure that we answer these queries correctly. So what we essentially have to do is learn all the queries that are made both during encryption of such a vector and during decryption with this vector V star. So what's marked here is as red. So if you think of these as being the sets of queries that we make, we have to learn this intersection in order to perform this decryption algorithm correctly. So how can we learn this intersection? Well, our idea is that we decrypt the ciphertext WI with all the secret keys that we have got in the game using the actual random oracle model and just observe the queries that happen there. And we hope that the queries we observe there are a superset of this intersection, so that they are enough when we learn them. So imagine for a moment we would not have this restriction that V star is not in the span of V1 to Vt, but instead V star and V1 to Vt are all uniformly random vectors. Then this argument would be relatively simple to do, because we can very informally argue, well, when an query made during encryption is very likely to be made during decryption for a secret key for a random vector, then it's very likely that we will learn this query also when we decrypt with one of the other secret keys that we got. And on the other hand, if a query made during encryption is very unlikely to appear during decryption with a random vector, then we probably don't learn it, but also probably we don't need to learn it because it's very unlikely that this query will appear when we decrypt with a secret key for V star. But for this argument, it's very important that the distribution we use for these vectors V1 to Vt and for V star is the same. Otherwise, it breaks down. And that's not the case here, because we have this restriction, V star is not in the span of V1 to Vt, so we have to use a very different distributions for these vectors V1 to Vt than for this vector V star. And so the main part of the work is to argue that this still works, even though these vectors V1 to V star are actually not chosen uniformly at random from the entire vector space, but just from a subspace that does not contain V star. And this problem can be phrased completely abstractly of cryptography, so you can forget all of the cryptography part now, because we can phrase this as a problem of extremal combinatorics. So namely what we have to show is if we have a function f that maps every vector from our vector space set q to the n, to some subset of a set of polynomial size. I like to refer to the set as the set of colors. So imagine we have a set of colors, and now we are assigning each vectors a subset of these colors. Then we want to show that with high probability, or overwhelming probability, that the colors we assigned for this vector y star are a subset of the colors we assigned to all of these vectors f of to all of these vectors yi, where again y star and y1 to yt are as before. They are uniformly random, conditioned on this y star is not in the span of y1 to yt. So the intuition here, how to connect this to the previous problem, is that this function f so f of y is this intersection. So we fix the vector we used during encryption and look at what are the queries that were made both during encryption and decryption for this vector y.
You say there exists a polynomial t, but you need to construct it, right? Like, you need to know what this polynomial t is in order to, or do you?
Not really. I mean, the adversary would have to know it, but we also just have to show that the adversary exists. So I think it doesn't matter if you don't have an explicit representation. Yeah.
Now, but actually, in the actual lemma, t can be expressed as a function of L. So once you fix L, so L denotes the number of queries of the encryption algorithm. So we have L colors. If you pick t large enough, but we can give a specific value to t, that t is L squared, for example, L squared will work. I'm just saying that.
Okay.
Yeah.
So it is constructed.
Yeah, it is actually constructible. Yeah. And so, yeah, that's the main ingredient that we need to finish the proof. And we provide several proofs of this in the paper. So first we consider a Vika variant that just says that these vectors y star and y1 to yt exists. So we don't talk about sampling them at random and this condition holds with some probability. We just want that they exist. And when we additionally make the restriction that the modulus is 2, then we can show this via a double counting argument. And for the average case variant, so that's the variant that we actually need, when we still have this restriction that q is equal to 2, we can show this using Fourier analysis. And finally, we managed to show it for arbitrary primes q using the Cauchy-Schwarz inequality, which then basically rules out all secret key IPFC you could think of. And yeah, so for the rest of the talk, I want to go into how we prove this lemma. And I want to use or at least start with the most simple variant here. So this existential variant for q equal to 2. So this result itself is, because it's just the existential variant, is not enough for our actual impossibility result. But I think it's very helpful to start with that because it already shows the main ingredients and challenges that you encounter. And this existential variant can also be phrased a bit slightly differently. And yeah, that's what I will do next. So what I want to show now is that if we have a function f that goes from zq to the n to these sets or subsets of this set of L colors, and we have that this condition here is violated. So we have that there exists y star, y1 to yt, such that y star is not in the y star is not a subset of these vectors 1 to t f of yi. So also in this setting, I've omitted all of these polynomial or with overwhelming probability. You can forget about all of that. And in particular, you can think of these vectors y1 to yt. Well, you can just pick a subspace of dimension n-1 and pick all vectors in that subspace. That's kind of the maximum you can, or yeah. That's all the vectors you could select without violating this condition, so why not pick all of them? And so I'm now interested in this condition. And if we can now find a lower bound on the number of colors that we need so that this can hold. So can we conclude from when this condition holds that the number of colors must be at least something?
Okay. I think there's a mistake in the description of the lemma because you're saying that if, so you're fixing the function and if there exists.
Yeah, that should be for all. So I want that for, sorry, yeah. I want for all y star and y1 to yt that satisfy this condition and this condition, yeah, that all vectors satisfy, with this condition also satisfy this. Then what's the, how many colors do we need to satisfy this? So informed means we have our vector space, we assign to each vector a subset of colors, and we want that when we pick one vector and one n-1 dimensional subspace, and that vector is not in the subspace, we want that this vector has some color that is not contained anywhere in the subspace. And yeah, but before I give you a lower, or the, yeah?
That can be arbitrary. Like, where does it use the fact that you're in a linear vector space?
So in the proof, we will use that it's a vector space. So actually, I shouldn't. The proof only works over for q equal to 2. So we're using that we're working over z2 to the n.
But the statement of the theorem has nothing.
The statement of the theorem, yes, that you can ask this for any vector space or other objects, but the bound we will get in the end only works for z2.
No, okay. So the place where we make use of the linear space requirement is where we say that y star is not in the span of those vectors, but that lemma holds for every function f. And you can think of that function f as the random oracle queries that are asked by the decryption algorithm. So
Yeah, and also during encryption. So
yes.
here, this
So
intersection.
f can be any complicated function. You don't need f to be a linear function.
Yeah.
So fix the function f, and if that condition holds, we want to prove that L cannot be small. L should be very large.
But like you said, if instead of span, you just take all vectors that are in that span, and instead of writing a span, you just write the list of all those vectors, then you're just making a statement about points, right? Like the fact that this is a vector space doesn't come into the question.
I mean, you need the vector space to, that this here makes sense, that y star is not in span.
Change the word span y1 to yt, so you just list all the vectors, like you said, that are in that span.
Yeah, but you still need to have a subspace here, like this cannot be an arbitrary set. It has to be, you can change this to being an n-1 dimensional subspace of z2 to the n. But it cannot be an arbitrary subset of z2 to the n.
Okay, keep going and I'll see if I understand more.
Okay, so yeah, maybe a good warm-up before I mention this lower bound that I want to show and prove it is to get an upper bound for this. So with how many colors can we actually find such a coloring that satisfies this? Can someone think of some coloring that will work? And you can use as many colors as you want. Sorry?
2 to the n, right?
Yeah, 2 to the n. So we could just use one color for every vector. So every vector gets its own color, then this is always satisfied. And yeah, we can also ignore that. So 2 to the n colors actually works. Actually, you can slightly optimize this because the 0 vector will always be in your subspace, so you don't need any color for that. So we can at least do it with 2 to the n minus 1 colors. Yeah, assigning one color to every vector is not the only option. There are many other ways to do it. So for example, I think also one other very natural way to do this is to pick every possible subspace. And then for every subspace, so every n minus 1 dimensional subspace, you pick one color and assign that color to every vector that's not in that subspace. Then you again have this property satisfied because, well, for every subspace, the color that you picked for that subspace is by definition not in that subspace, but every color not in the subspace has it, so that also satisfies this. Then we need as many colors as there are n minus 1 dimensional subspaces, and that are again 2 to the n minus 1, so it's the exact same bound. And that shouldn't come as a surprise because what we can prove is that that's already optimal. So we actually need 2 to the n minus 1 colors. You can't do it with less. But for the proof, I will first start with something somewhat simpler bound that is not tight and just shows that L is at least 2 to the n minus 1 divided by 2. So we will use a factor of 2. Maybe you can spot where this factor of 2 gets lost. Okay, so before I want to prove this, I want to prove a claim. And that claim says that for every set S that's not the empty set and a subset of set 2 to the n, so this now doesn't have to be a subspace, it's any subset. And there are at most 2 to the n divided by size of S subspaces V of our vector space that 2 to the n that have dimension n minus 1. And have an empty intersection with S. So why is this such a result helpful? Well, think of S being the set of all vectors that have a certain color. Then we want to count how many subspaces of dimension n minus 1 we can now find where this color doesn't appear. So at least with respect to this one color that we look at, this condition here would be satisfied for a vector in S and that subspace V. Okay, so let me first prove this claim.
So in the claim, S cannot be empty. You said S is
yeah. Sorry about that. Yeah, S should not be empty. Otherwise, we're dividing. So that's just to avoid dividing by 0 here. And the idea is here that whenever we have such a subspace of dimension n minus 1, we can describe it by a single vector that's orthogonal to all the vectors inside that subspace. So such a subspace can always be described as so a subspace of dimension n minus 1 is just all the vectors V such that the inner product between x and V is 0 for some vector x. So in Euclidean geometry, this would be the vector that's orthogonal to your plane. So we now identify all of these subspaces with these vectors, and I call them, let's say we have t such subspaces, then I can call these vectors x1 to xt. So maybe I should use a different variable because t has nothing to do. Let's call them tau, x1 to x tau. And yeah, so let's say I get via this vectors x1 to x tau. Now, if I have so many vectors, or any vectors, any tau vectors, I can argue that at least log t of them must be linear independent. So we have at least d, which is log t. Linear independent vectors. Okay, now we want to, so yeah, we started with a bunch of subspaces. We have for each of these subspaces, we've picked this vector that's orthogonal to the subspace. We have found, since we started with tau subspaces, we have found tau such vectors, and now figure out there must be log tau of them that are independent. And so how does this help? Well, we now want to count how many vectors are in none of these subspaces. Well, in order to be not in one of these subspaces, you have to violate this. So these vectors v, or these vectors, let's call them s because they will be later in s. These vectors s that are not in any of these subspaces must satisfy that the inner product between xi and v is equal to 1 for all of these x1 to xt, in particular for these linear independent vectors. Which means that these vectors that are in, sorry, I wanted to call them S. These vectors that are not in any of these subspaces must live in an affine subspace of dimension n minus d, where d is this. And that gives us an upper bound, how many there are. Since they are in the subspace, we can have at most 2 to the n minus d of them, which, if you now plug in this, means they're 2 to the n divided by t. And this can be rearranged to this claim. Okay, now let me briefly sum up with how can we use this claim to prove the actual lemma that we want. Well, that's very relatively simple now. We just have to use this double counting technique, and what we count is the number of triples C, Y star, and V, where C is a color, Y star is a vector, V is a vector space of dimension n minus 1, with this usual restriction that Y star is not in this n minus 1 dimensional space. And we want that C is in f of Y star, but C is not in the union of these vectors Y. So our condition that we have in the lemma says that the number of these triplets must be at least 2 to the n minus 1, because that's the number of subspaces we can choose for V, times 2 to the n, 2 to the n minus 1, because that's the number of vectors y star we can find that are not in the subspace, kind of times 1, because for each of these combinations we need at least one color that violates this condition. So this gives us a lower bound on the number of triples, and this claim gives us an upper bound on the number of triples. And the claim essentially says that the number of such triplets is at most the number of colors times 2 to the n. Just here, I mean, multiply this by the size of S, then you get, okay, the number of vector spaces times the size of S is at most 2 to the n. That's what where this 2 to the n comes from. And if you rearrange this, or put these together and rearrange this, you get that the number of colors L is at least 2 to the n minus 1 divided by 2. Which proves this weaker version of the lemma. So did someone spot where this factor, how we can get rid of this factor of 2 and tighten the lower bound? So we can actually not allow, or these x1 to xt, they cannot be arbitrary vectors. They actually have to be, so these vectors x1 to xt, they must form a sum-free set, because as soon as we would find here vectors xy, xi, xj, and some sum of them, so xi plus xj, we would have that every vector, or no vector could satisfy this condition for all three of them. Because if you have, if xis is 1 and xjs is 1, then the inner product of xi plus xj and s is 1 plus 1, so 0. So that then would be in one of the subspaces. So these x1 to xt must be a sum-free set, and the maximum size of sum-free sets is essentially in a vector space is not 2 to the n, but 2 to the n minus 1. So then we get a 2 to the n minus 1 here, and then we can get rid of this factor of 2 here. And then the lower bound becomes tight. Well, for the q equal to 2 setting, that doesn't matter as much, because it's just a factor of 2. But when we want to generalize this for arbitrary modulus, this kind of problem becomes important. And so it becomes important to take care of it. But unfortunately, it's not that easy to take care of it anymore, because this nice condition that they are just a sum-free set becomes more complicated over larger moduli. Yeah. Okay, that's it from my side. Do you have any questions?
Thank you. If you have any questions, please wait for the mic so the recording picks it up. I have a really simple question about this last slide. So if the existential variant is weaker, but you have only shown the harder version, do you mean like the Cauchy-Schwarz, like you didn't bother proving the weaker version, it just was implied by the stronger one? Or?
You mean here this empty spot in the table? I think I didn't include it because I found a different paper that proves this. And so, yeah, you can, of course, prove it and get also interesting bounds. I think there are several papers that prove, I found at least one that proves something like this. And that was also the main inspiration to prove our average case variant. So, I didn't include it there because it wasn't a contribution of the paper, but yeah, of course, you can do it.
Yeah, I have a question. This solution is the unique question to the unique solution to this to the question that you mentioned at the beginning of your presentation. I mean, you said that you want to know about f of m. So why? Let me ask in another way. I'm looking for example, to see that, for example, FHE can help us here or not.
Sorry, that it?
Fully homomorphic encryption systems can help us here or not?
Yes, so fully homomorphic encryption solves a related problem to functional encryption, but it can be used in slightly different contexts. So fully homomorphic encryption is usually used when you want the cloud server to do computations. In the setting I presented, the cloud server was actually not doing anything, was just storing the ciphertext and sending it out again. So it was not doing any computations on it. That's usually what you use fully homomorphic encryption for. But with fully homomorphic encryption, you cannot give this partial access. So with fully homomorphic encryption, you could have the cloud compute f of m and maybe send the ciphertext of f of m to Bob. But then Bob would again need the key for your fully homomorphic encryption scheme in order to decrypt it. So you would still have the problem that you have to give Bob the key for the entire scheme. So when you trust the cloud to send only the ciphertext for f of m to Bob, it also solves this problem. But you are having now an additional trust assumption on the cloud server, because if the cloud would behave malicious and send Bob the entire encrypted database, Bob could again learn more. So yeah, it's related but incomparable.
Great, thank you. We're out of time, so let's thank Roman again.